Hello students, welcome to my YouTube channel. Today we are going to discuss a very important theorem of complex analysis which is called Liouville's theorem. Liouville's theorem actually states that any bounded and entire complex function must be a constant. So it actually states that any bounded and entire complex function will have a singleton set as its range. It is a very shocking result as far as real analysis is concerned, because we know there are plenty of real functions which are bounded and analytic all over real field R, but yet they are non-constant functions. For example, we can have sin x and cos x. These functions are bounded obviously. Why? Because we know that sin x mod is less or equals to 1, cos x mod is also less or equals to 1. So they are bounded. Also we know that they are differentiable all over R. So they are entire, but yet they are non-constant functions. So Liouville's theorem doesn't hold true for real functions. It only applies to the complex functions. So what actually Liouville's theorem states? Liouville's theorem actually states that suppose fz be a complex function. This should be a complex function. Okay. Now it should satisfy two criteria. First, there should exist a finite real number capital M such that fz mod becomes less or equals to M for all z belongs to the complex set C, and it should be analytic throughout, fz should be analytic throughout C. So this criteria means fz is bounded and this criteria means fz is entire. If these two condition holds true, then we will have fz equals to constant for all z belongs to script C. So this is the statement of Liouville's theorem. Now in this video we will first prove the Liouville's theorem and then we will check out some applications of Liouville's theorem in complex analysis. So first we prove Liouville's theorem. So what are the hypotheses? The hypotheses are fz should be bounded and entire. These are the hypotheses of the theorem. We have to prove what? We have to prove that fz is a constant function. We have to prove this. So since fz is bounded, we will have a finite real number capital M belonging to R such that fz mod will be less or equals to capital M for all z belongs to script C. This is the definition of being bounded of a complex function. Then we assume an arbitrary complex number, suppose A. This is a very arbitrary complex number A, and we also assume a curve gamma such that gamma is equals to z, where z is equals to r e to the power I theta, where theta starts from 0 and ends at 2 pi. So this is obviously gamma means a circle whose center is at origin and whose radius should be capital R. We choose A in such a way that modulus of A is less than capital R, and capital R is a finite real number. So this is less than infinite. So we can have a diagram here. This will be our curve gamma, where this is the circle's radius R and this is the center of the curve gamma. Now since modulus of A is less than R, it may lie here, it may lie here, it may lie here, or it may lie here. So it actually means that A will be an inside point of the closed curve gamma. Now since the function fz is entire, we can say that fz is analytic inside and on the closed curve gamma as well. So by Cauchy's integral formula, since A is an inside point of gamma, we can have fa equals to 1 by 2 pi I integration over gamma fj divided by z minus a dz. This is the Cauchy's integral formula. Also, since origin means 0 is an inside point of gamma, we can also have by Cauchy's integral formula f0 equals to 1 by 2 pi I integration over gamma fz divided by z minus 0 as well, okay, into dz. We are not writing minus 0 because it gives only z. Now if we subtract f0 from fa, what we will have? We will have fa minus f0 equals to this minus this. So 1 by 2 pi I is in front of both the integration, so we are taking this as common, 1 by 2 pi common taken. Now over the curve gamma integration being done, fz by z minus a minus fz by z. So fz is being common in both the terms, we are taking it outside the bracket, and inside the bracket we are having this subtraction 1 by z minus a divided by 1 by z into dz. So if we perform this subtraction, we will have what? We will have fz in the numerator, and after subtraction there will be an LCM in the denominator, z into z minus a. We will have z minus z minus a, so it will be only a, z cancellation, after z cancellation. So this is our a, which is a fixed arbitrary complex number, so we can take this a outside the integration, so it may lie here. So we are having what? fa minus f0 is equals to a by 2 pi I integration over fz by z into z minus a dz. Okay, now if we take the modulus of this, then we will have this will be equals to modulus of this. Now modulus of this means what? Mod of a in the numerator, and 2 pi I mod means 2 pi. Okay, and we will have mod of this integration over gamma fz divided by z into z minus a. Now if we remember Emil's inequality, what Emil's inequality says? Emil's inequality says that if the inside of the integral, if this portion have a maximum value on gamma m, suppose m being the maximum value, then this modulus of the integration will be less or equals to m into the circumference of the curve gamma, or the length of the curve gamma, ml we write. So in this case, this portion will be less or equals to what? Mod a divided by 2 pi. Fz has the maximum value m. Okay, so fz mod is less or equals to m means what? Fz mod will be less than m, and z, maximum value of z in the curve gamma will be equals to r, because gamma is a circle with radius r. So this z can be replaced by r, and z minus a can be replaced by r minus mod a into the length of the curve gamma. Gamma is a circle with radius r, so this will have a circumference 2 pi r, which is the length of the curve gamma. Now r cancellation gives, and 2 pi cancellation gives mod a into m. So we will have what? We will have fa minus f0 modulus is less or equals to m into mod a divided by r minus mod a. Now if we make this r sufficiently large, so if I make r tending to infinity, all the other terms are fixed terms, so this part will be tending to 0. This means what? When r is infinite, so if the curve gamma is encircling the whole complex plane, then this part becomes equal to 0. So we will have what? Fa becomes equals to f0. Now f0 being a constant number and a being an arbitrary number, so it implies that the function f at any arbitrary point a gives equal value of the function at the point origin. So it is nothing but a constant. So this is our theorem of Liouville's theorem. So here we have done the proof of Liouville's theorem. Now we will see a very interesting application of Liouville's theorem in complex analysis. And what is the application? The application is, suppose f being an entire complex function and fz mod be greater than m for all z belongs to C. If these two criteria holds, then only we can write fz is a constant function. So in this case, the boundedness of the function is not required. Only this criteria is replacing the boundedness condition of Liouville's theorem. So the function should be in such a way that modulus of fz should be greater than a finite real number capital M, and here m should be greater than 0 obviously. So it is actually meaning what? It is actually meaning that the function fz always takes value outside a particular circle with radius capital M and center at the origin. So fz is lying outside the circle this, then only fz will be equals to constant. So we can prove this by Liouville's theorem as well. Liouville's theorem means what? Liouville's theorem gives if f is entire and if f is bounded, then f is constant. Now here we are not given the boundedness condition, we are given what? We are given this. Now since fz is entire and mod fz is greater than m, so fz is not equal to 0 anywhere, since fz mod is always greater than m. Now we can tell that 1 by fz is also entire then, and since mod fz is greater than m, 1 by mod fz will be less than 1 by m. So we are having what? We are having 1 by fz, a function which is entire, and 1 by fz is also bounded. So we can conclude by Liouville's theorem this is a constant function. So 1 by fz being a constant function gives fz also constant. So this is our application. Now we will check whether the boundedness condition in Liouville's theorem is a necessary criteria or not. Simply saying this is not. Why? Because we can replace the boundedness condition in Liouville's theorem by a very simple condition. What? If fz be entire and real fz or imaginary fz being bounded. So we are not needed fz to be bounded. We are just needed the real fz or the imaginary fz portion to be bounded. Then only fz will be equal to a constant. We can prove this easily. How? If we can suppose phi z being another function which is equals to e to the power fz. Now since fz is entire, we can conclude phi z is also entire. Now here we are having what? Phi z mod will be equals to e to the power fz mod, and what we given? E to the power fz mod means e to the power real fz. Now since real fz being bounded, e to the power real fz is also bounded. Okay. Now since phi z is entire and mod phi z is less or equals to m, we can conclude that phi z is entire and phi z is bounded as well. So by Liouville's theorem, phi z is a constant function. Now if phi z is constant, we can have phi dash z, which means e to the power fz into f dash z equals to 0. Now e to the power fz can never be equal to 0, so f dash z is equal to 0. So f dash z equals to 0 for all z belongs to script C, because this happens all over C. So fz becomes constant. So we can conclude that the boundedness condition of Liouville's theorem is not a necessary criteria. We can replace the boundedness condition of fz by only the real fz or the imaginary fz being bounded or lying at a half plane. This is the another application of Liouville's theorem. This is all we have in this video. Thanks for watching. Please like, share and subscribe my channel. Press the bell icon for more such updates. Thanks. Thank you very much.